So in today's lecture, we're going to talk about other ways to determine our enthalpy, heat of reaction, or delta H. These are three different ways we've referred to it. And so we've already learned two ways to do so. One, using reference table I, and then we just look up a reaction and read its delta H off the table. And then also we can use potential energy diagrams to look at the difference between the energy it took to break the bonds and the energy that it took that was released when you formed the new ones. And so what we're going to learn about today are two different ways to figure out enthalpy. The first of which is where you combine individual heat of formations of all the compounds in the reaction. So we'll talk about what a heat of formation is next. And then we're also going to look at combining equations using what's called Hess's law. And that just says, regardless of how many steps it takes in a reaction, the total change in enthalpy is going to be the sum of all the changes. And so we're going to look at first defining heat of formation. And this is just the energy absorbed or released when a compound is formed from its elements. So this is the energy associated when you're forming a compound. And so these are always measured at the standard conditions of 1 atm, which is pressure, and 298 Kelvin for your temp. And so we use this symbol, which is H, and then, delta H, degree sign, little f. So this is heat of formation. And so single elements, they have a value of 0 for their enthalpy of formations because they're not forming compounds, they're already at their elemental state. And so we use this reference table B here. So this will be in your notes. And so you can actually look up different heat of formations for different compounds. And so in order to find our enthalpy, and so we talked a lot about just calling this delta H, I'm going to give it this little subscript here of RxN, which just stands for reaction. And so when we're figuring out the enthalpy of a reaction, we need to make sure to multiply our heat of formations by the coefficients in our balanced equation. And so I'm just going to jump right into an example of how we use the heat of formations to determine enthalpy. And so if we're looking at the reaction where calcium carbonate goes to calcium oxide plus carbon dioxide, we are given in the problem that our heat of formation of calcium carbonate, so that would be our delta HF of calcium carbonate, is negative 1207 kilojoules per mole. And we're also given that our heat of formation of calcium oxide is negative 636 kilojoules per mole. We weren't given the heat of formation for carbon dioxide, so we have to look it up in table B. And so if we go to the right and find carbon dioxide, which is here, we then find that its heat of formation is negative 393 kilojoules per mole. And so I'm just going to write that down here. Now, we need to also double check that our equation is balanced. And so if we look, we have 1 calcium on both sides, we have 1 carbon on both sides, 3 oxygens here, 1 plus 2 here is 3. So the coefficient in front of all 3 of these species is 1. So that's good. And so I'll show you where we incorporate those coefficients in this reaction here. And so let's start using our equation. We have delta H of reaction is equal to the sum, that's what epsilon means, of our heat of formation of the products minus the sum of the heat of formation of our reactants. And so I'm going to use the same curly bracket here. And so I'm going to start with my products. So I'm just going to start with calcium oxide. And so what it says is we have 1 mole, and where this comes from is the coefficient from the balanced reaction. That is going to be multiplied by its heat of formation of negative 636 kilojoules per mole. We are then going to add the other product together, which is also 1 mole, as all of their coefficients were 1, multiplied by negative 393 kilojoules per mole. So this is CO2. We are then going to subtract the sum of the reactants. Well, we only had one reactant, which was 1 mole times negative 1,207 kilojoules per mole. All right, and so writing it again, this was calcium oxide, this was CO2, and this was our calcium carbonate. Moving on to the next one. If we were to have numbers, this is where I'd suggest to do all your multiplication and whatnot. I'm just going to simplify the product term. I'm going to put this different color. So I'm going to simplify the product term. If you do that, you get negative 1,029 kilojoules. And we're subtracting our reactant term, which is negative 1,207. And so you guys should know if you subtract a negative, you're really adding it together. And then our answer is positive 178 kilojoules. So this is how you can find the heat of reaction just by using the heat of formation for compounds. Let's do another example here. So this one has to do with potassium chloride reacting with oxygen to make potassium chlorate. And so we're given that the heat of formation for potassium chloride is negative 391. And so the formation for KCl, we'd look that up in the table, and you would find that that is negative 436 kilojoules per mole. What would it be for oxygen? Because if you look at the table, oxygen's not on the table. Reason being, because it's an element. Elements don't have a value associated. They're just 0. And so when we go to use this equation, again, we're going to start with the products. So delta H of reaction is equal to, can we just use 1 mole here? No. So where I'm going to pull this coefficient from is, so if we're on the product side, I'm looking at this product, and I'm going to pull this coefficient of 2. That's going to be our 2 moles. So we're going to do 2 moles multiplied by its heat of formation of negative 391. We are going to then use our curly bracket because that's our only product. Now we're going to get ready to subtract our reactant term here. And so if I'm looking at, let's just pick on potassium chloride. So we're using this compound and this coefficient here. And so this one says for every 2 moles, we're going to multiply that by negative 436 kilojoules per mole. Or add that to our other reactant, which would have the coefficient of 3 moles, but because it's just O2, that is just going to be 3 times 0. So this term will end up dropping out. And then end with our curly bracket. And so again, if we take that step to simplify our terms, you will get that our products come out to be negative 78 kilojoules, because we multiply, oops, sorry, not 78, 782 kilojoules minus a negative 872 kilojoules. And so you get that our delta H of our reaction is equal to a positive 90 kilojoules. Okay, so that was one additional way we can figure out delta H. Now we're going to talk about using Hess's law. And so, mentioning it again, if you have an enthalpy of a given reaction, it is constant no matter how many steps it takes to get to the end. And so Hess's law then states that if you have a series of reactions that you add together, the enthalpy for your net reaction will then just be the sum of the enthalpies of the individual steps. And so you have to remember when we are manipulating these reactions that we are changing the delta H. And so we'll discuss the steps kind of to go about these problems here. And so typically how these problems work is you'll be given a reaction and be asked to determine delta H. You'll be given at least two other reactions that you're going to have to manipulate. And then you're going to add together. And what I mean by manipulate is either you maybe multiply them by a constant or you reverse the reaction. And so the main rules here are if you reverse a reaction, then you must reverse the sign of delta H. So if it was positive and you flip the reaction, then delta H is now negative. You also have to remember when you're adding equations, you will cancel out quantities of species that are on opposite sides of each other. So if you have a species that's 1 mole on the reactant side on one equation, 1 mole on the product on the other, those actually cancel out. And then you have to add the species if they are both on the reactants or product sides of the two equations you're adding together. And so, of course, you must have the correct products on the right side of the arrow and reactants on the left, that's where they belong, and no other compounds can be in your equation if they're not in the one you're trying to match. Lastly, make sure that the coefficients match. So if you're supposed to have two moles of something, you only have one, you did something wrong. And so once you're done manipulating and adding up, you find the target equation, you add up all the enthalpies. And so I wanted to put a little note in here, like, why do we care? So there are certain chemical reactions that we just can't duplicate in the lab. My example here is the way that acid rain forms from a volcanic eruption. You just can't do that in a lab. So Hess's law actually gives us the ability to calculate the enthalpy related to it because we can add reactions that we can do in the lab to get our final target reaction. And we're going to actually practice with this example. So the target equation for the formation of acid rain is 2S plus 3O2 goes to 2SO3. And so we want to figure out what is our delta H. And so the equations given to us are labeled equations A and B here with their respective enthalpies. And so starting off, right away when I look, I notice that there's a 2S in my target, and the equation I have that relates sulfur only has 1. So I'm going to decide to double reaction A. And the key here is when you double a reaction equation, you have to double all the coefficients for everything as well as delta H. So how I would write this then is if we were to give this a big 2 in front of the whole entire thing, we're going to call this reaction C. We are going to get 2S plus 2O2 goes to 2SO2. Our new delta H is going to be 2 times negative 297, which gives us negative 594 kilojoules. Okay, so now at least I have 2S both on the reactant side. As I'm looking at reaction B, I notice right away that SO3 is on the reactant side when it should be on the products for my target equation here. And so I'm going to go ahead and reverse the equation. If I were to reverse it, I now have 2SO2 and O2 as a reactants, and then I have 2SO3 as my product. And when you reverse a reaction, I'm flipping the sign now to negative 198 kilojoules. Now, I'm going to see if I have done enough work. I'm going to add up our two new reactions, C and D. So I'm going to rewrite them down below. C is 2S plus 2O2 goes to 2SO2 with a delta H equal to negative 594 Kelvin. D is 2SO2 plus O2 goes to 2SO3 with a delta H of negative 198 K. So now, the rule that I was explaining is if you have a species in the products of one equation that's in the reactants of another that you're adding together, they cancel out. So because you have 2 SO2 here as well as 2 SO2 here, these terms actually cancel out. Then, remembering that we are adding these equations together, if you have two that are on the same side, like O2, this is really like a 2 plus a 1, and so the term that we get of adding our oxygens together then would be 3O2. And so we have to bring down our 2S. Our reaction arrow goes to 2SO3. And if we check our target equation, which is up here, these match. So then all you have to do is add the enthalpies together. So negative 594 plus negative 198 gives us a grand total of negative 792 kilojoules.